All right. Our next speaker is Dale Schuurmans. Dale is a professor at the University of Alberta and also a researcher at Google Brain. His interests include machine learning, optimization, and search. Please, Dale.
Oh, okay. Hi. Thanks. Pleasure to be here. So I'm just going to tell what I think is a simple story. It won't be very technical, but it's something that's been vexing me recently, and I wanted to maybe run this by you to see if you can help me make sense of things. Okay, so right at the very heart of reinforcement learning, there still exists a fundamental problem, and it's this thing known as the Deadly Triad, and it's still with us. It's this problem that you cannot combine these three things. Generalization, that is, we'd like to take experience over a small subset of the state action space, and take that experience and extrapolate it over, a full environment. We'd like to also do off-policy learning. We'd like to be able to use data from other policies, other collection policies, log data, you have it. And we think we'd like to bootstrap. That is, we'd like to use temporal differencing or Bellman consistency concepts, various ways to sort of formulate solution techniques. And the catch is that these three things together are provably unsound. They're unstable and worst case divergent. So of course this lies right at the very heart of current dominant methods in the literature. Now, of course, reinforcement learning is a big field. It's growing rapidly. And there's this proliferation of extensions and improvements to things like DQN, double Q, distributional, multi-step backups and so on and so forth, all kind of wrapping this unstable core in sort of layers and layers of stabilizers, none of which are guaranteed to actually resolve the problem right at the center. Now, this worst case instability is not just an academic concern. It actually impacts the real practical utility of these techniques. I'm sure you're well aware of the fact that for naive end users, it's almost impossible to take something like DQN or Rainbow off the shelf and apply it to a new scenario and robustly and reliably, get it to work without a lot of expertise. So, a lot of us have been, trying to kind of, revisit this problem. It's been with us for decades. I've given it a few tries. But what's been interesting is recently there have been, some bits of progress on understanding the nature of these fundamental issues in reinforcement learning. Tyler Liu gave a nice talk a few days back about some of our progress here. And I just want to maybe share a little bit about one of the trajectories that's sort of followed since then. So we'd like to break this Deadly Triad, which basically means we've got to give something up here. Well, there are not that many options, right? You could look at it simplistically. We could, for example, give up on generalization, but actually of the three options, that's the one thing we really, really insist that we want to keep. You could give up on off-policy data, right? And simply be on policy, and this is, a legitimate thing that is the source of the other major, area of reinforcement learning technology around on-policy methods and variations thereof. Which brings, this side effect of being somewhat data inefficient because we're trying to, sort of exploit data only by its relevance to current policy. What I actually want to talk about is the only other option on the table here is to give up bootstrapping and to actually try to exploit generalization and off-policy data. What's really surprising to me at this age is to discover that I'd never really thought about this problem, and actually the literature on this trajectory is it's not empty, and apologies to those of you who've worked on this already, but it's a vastly smaller literature. So this is the road less well-traveled, but it actually turns out to be a very interesting road, and so I want to sort of advocate a little bit for some attention to this trajectory. To be a little more concrete, what I'm going to think about specifically is the problem of batch policy optimization from log data. So you've just gathered some data in a log. That's it. That's the data. It's batch. You're not going to get more data. There's no exploration. You're just simply going to optimize your policy based on that information. What's interesting about that task is because it eliminates exploration as a concept, is it looks an awful lot like the rest of machine learning. It really is a problem where generalization is key. If you generalize, you do well. If you do not generalize, you will fail. Interestingly, and I've kind of floated this by a few people, there's a sense in some parts of the RL community that this is just simply impossible. And my reaction is that is actually how the rest of machine learning works. You take data from a subset and you fit or optimize the model on that data, and you really expect it to generalize and perform well on data that you've never seen. And so another way to phrase this is, this quest is, can we actually make better use of generalization in reinforcement learning, or are we actually already maximally exploiting it? And my claim is going to be no, that we're actually leaving a lot of very useful techniques on the table by not recognizing some basic connections. So what I'm going to do is organize the rest of this presentation, I may have to speed up a bit, into two parts. I'm going to start out with a simple single-shot decision-making scenario, and just sort of talk through the relationship between batch contextual bandits and classical supervised classification learning. Notice that there's some strong similarities there, and exploit that connection to maybe understand a little bit about how we might do better generalization in batch contextual bandits. Once we've got that in place, I'm going to give you some pretty preliminary speculations about how we can use these outcomes to improve generalization in the full sort of sequential decision-making case, and actually use generalization as a proxy for bootstrapping instead of bootstrapping, and see how far this goes. This is an actual workshop talk. Like, I literally made these slides yesterday. I was running experiments through NeurIPS. It's kind of live. Anyway, okay, let's see how this goes. So single shot decision making. So here's the problem. Okay, I give you a bunch of log data, and it's a contextual bandit setting, so I log a bunch of context X. In each context X, you took some action A and you log the reward R. And we'd like to just look at this data, process it, and produce a policy, a mapping pi from context to action. That's it. Now, often what people really desperately want to do is say, okay, but just tell me you also log the proposal probabilities, the probability with which you took action A1 in context X1. Please, please, please give me the proposal probabilities. And why, might you ask, do they care? Because sort of the dominant approach right now, or the way to think about this problem that seems to be prevalent in the literature, is that what you want to do is formulate unbiased estimates of expected reward. Through some basic importance correction techniques. Now, there's lots of variations on importance corrections, variance reduction strategies, but the thinking is you want to formulate an unbiased estimate of expected reward. That's what you want, and then optimize that. And here's what sort of puzzles me, is that we know that's a bad idea, and so I guess I'm trying to get your attention. But we've seen this idea before. It was decades ago, and it was not effective. And the reason it's not effective is not about variance reduction. There's actually a deeper problem, which is the underlying optimization landscapes you create in such an approach is very, very difficult to work with. To make the case, at least the way I'm seeing it, the easiest way to understand the difficulty is to understand the relationship between what we're trying to do here in a batch contextual bandit setting and just the simple classical supervised classification learning problem that you all no doubt learned in the second lecture of your first machine learning course. So here I'm using MNIST as a simple example, but I just want you to notice side by side, on the left we have a fully supervised task where we have contexts, we have a fixed set of actions, you might know them as labels, and in the supervised case we've just simply logged for every possible action in every context in the data set what the reward would have been. Say we're interested in 0-1 misclassification. The only real distinction between supervised learning and contextual bandits is in the contextual bandit setting, we haven't systematically logged, counterfactually, the reward for every action in every context. We just maybe logged one or a few actions for every context and the rewards that were associated with them and left the rest unobserved. The classifier or the policy are the same object. The data is almost the same data. It's just this completeness on the rewards. Okay, so I just want to get you to think back to supervised learning. And ask yourself a simple question. If you're interested in minimizing misclassification error, when in your experience did you train a supervised learning algorithm to minimize an unbiased estimate of misclassification error? When was the last time you directly minimized misclassification error? And the answer is you haven't, unless you're at least my age. And the interesting thing is, why not? It turns out there's no technical reason why you couldn't do this. It's actually perfectly feasible. It's a differentiable objective. You could just pull gradients through it, optimize your parameters, away you go. This was an idea that was actually presented at NeurIPS in the late 80s, maybe early 90s. And the conclusion is it doesn't work that well. And how is that true? Because the optimization landscapes you create are ineffective. And maybe instead of drawing a cartoon, the quickest way to get you to see this is at the output layer of your neural net, you're going to have a softmax transfer, mislabeled, but whatever, right? You're going to exponentiate and renormalize. If you add a temperature parameter to that exponentiation, take the temperature to 0, becomes the 1 hot. In the 1 hot case, that optimization objective is piecewise constant. The only thing that's happening by reducing, moving the temperature from 0 is you're taking a piecewise constant landscape and smoothing out the edges a little bit. It's a horrific landscape. When you watch the training curves, it saturates, you think, oh, it's done. And then, oops, on to the next plateau, next plateau. It's all plateaus everywhere, almost everywhere, okay? It really just is not that effective. This is what's hiding behind all the variance that's got everyone distracted, okay? So why have you never done this? Because by the time you probably took your machine learning course, you were confronted with the natural response to this, which is to use various surrogate objectives like hinge loss, or nowadays like log loss is back in favor. What these objectives are not unbiased estimates of misclassification error. They are biased in that sense. But what they do is they provide good optimization landscapes. They're almost always convex, at least at the output layer. And what we're trying to do in supervised learning, we know this, we trust it, is we're trying to generalize. We're trying to exploit the fact that if you can train in this proxy objective and get that objective small, that will translate into small misclassification error, at least you hope, and that will transfer from your training set to your test set. And we believe in this in the supervised case. What's shocking is that for some reason we don't seem to trust it as much in the reinforcement learning case. And I'm going to actually just sort of entertain the hypothesis that maybe we should be trusting it there as well. Okay, so what does that look like? So I'm just going to show you a quick study in what surrogate objectives might look like for, say, contextual bandit optimization. Just to set the groundwork, I got to start with the supervised case. So I'm just going to sort of use 4 canonical loss functions as sort of the basis, and maybe I'll do this somewhat quickly. If for a given example, we have like a vector across actions, and we can assume we have a reward vector across actions. In the supervised case, we see the full reward vector. Pi will denote the output layer, our probability vector, output by our model. So expected cost would be like minus expected reward. And that's a differentiable objective. You could certainly try to optimize that objective. You could, try to minimize squared error. You could take the squared difference between the logits. You could, hope that those could serve as action value approximations and just minimize squared difference to the rewards. Or you could do these 2 important KL divergences. The first KL divergence there is the label smooth maximum likelihood form. It may not look familiar to you, but what this is doing is simply taking the reward vector and using that to infer a target distribution. Instead of just taking the 1 hot target distribution, though, what you really want to do is exponentiate, use a temperature parameter to kind of sharpen or soften as needed, and renormalize. So map R into a target distribution p hat, and then minimize the KL divergence p hat to pi. This may look obscure. This is label smoothing. So the hard 0-1 maximum likelihood usually doesn't work as well, or doesn't confer as good generalization as what people call label smoothing, which seems like an egregious hack, but label smoothing is simply introducing a temperature parameter to the map from the reward to the target distribution. That actually works really well in supervised learning, tremendous generalization benefits. When you flip that KL, which apparently we're taught never to do, but anyway, let's do it, you get something interesting, and again, might be hard to see, but what you get is entropy regularized expected cost. So it really is just adding an entropy regularizer to that first objective gives you that KL at the bottom. That KL at the bottom looks really natural in an RL context. It's never used in supervised learning, as far as I can tell, but it actually works okay. Get to that in a minute. So imagine we have this framework, and now we want to get to, well, that's just wonderful. Hang on. Okay. And now we want to get to contextual bandits. So what's the issue? The issue, of course, is that you no longer get a completely specified reward vector, and we're going to have to now formulate, surrogate loss objectives that, deal with just partial observations. And just for the sake of argument, I'm going to pursue something like just incredibly simple-minded. Which is all I'm going to do is just simply impute or make guesses about all the missing rewards, right? So say you see one reward in a given context, we're just going to fill in the rest somehow. One natural way to impute is just, okay, take an importance corrected unbiased estimate of reward, that first sort of set of equations there, which is an unbiased estimate, but it's actually a really poor imputation strategy because what it does is it produces a sparse filled reward vector. It fills everything in with 0 except for the thing you saw, okay, and then rescales it. A more interesting thing, and something that's actually used in Contextual Bandits, is this thing called Doubly robust estimator, but it's simply this equation at the bottom, which is you can plug in any imputation vector you like, Q, and then you can add this unbiased correction factor you can add this correction factor so that in expectation for any Q with this sort of weighted shift, you get an unbiased estimate of the original reward R. This is a much nicer imputation mechanism. In fact, what I'm going to do is I'm going to use it in a self-imputation framework. So whenever I encounter an output distribution or reward I'd like to impute, I already have a model. My model is going to produce logits, which we could think of as action values across everything. And I'm just going to use the doubly robust estimator with respect to the model itself. Self-supervised, okay? Sounds like a bad idea, perhaps. But then we're just going to take that strategy and we're just going to plug it into these 4 objectives. And now we have differentiable objectives that we can apply to, like, partially observed log data. And just go with it. Okay, that was almost a clean story. There's only one other thing that happened is in sort of, floating this trial balloon around a little bit, I started encountering people proposing all kinds of hybrids, like, oh, well, maybe you could mix least squares with expected cost and so on. I thought that was all like daft. It made no sense. It was unprincipled until I tried it and decided that you better consider these. So you can also consider a family of pretty much any convex combination of those previous things I showed you. Okay. It does seem unmotivated. Just at the bottom I could pitch a little bit, and this appears like in some appendix of some paper from a few years ago that we put together. In the non-zero temperature limit, you can relate the 2 directions of the KL to each other, and it's in fact kind of nice that at temperature tau, you can take a convex upper bound of the non-convex orientation of the KL divergence. So I can upper bound one orientation, the entropy regularized expected reward orientation of the KL divergence, by the reverse KL, which is the maximum likelihood orientation, plus a scaled quadratic. It's just a second order Taylor analysis. And this gives you a nice convex upper bound to the original non-convex objective. That also has a nice property that it's unbiased. That is, it doesn't deflect the global minimizer. So it's really like modeling the, giving a nice sort of quadratic or convex model of the optimal region. And in fact, you can use this to motivate most of these hybrids. Okay, anyway, let me move on. So at this point, I wasn't even sure myself if I'd lost my mind. I was asking people, like, where's all the papers that I've been missing? And I probably still am, and please, be kind. I mean to cite your paper, just let me know. But I wasn't clear any of this made sense. So, let's just run an experiment. So you just take MNIST, why not, start somewhere. And just run a simple experiment. So, you've got your 55,000 training examples, hold out some for validation. You've got 10,000 test examples. On the training data, how about we just do the simplest thing? We'll just randomly pick one label per image. And if that's the correct label, you get reward 1. If that's the incorrect label, you get reward 0. So indeed, you're only going to get about 1/10 of the correct labels, right? A very, implicitly a very small training set. So be it. That's your batch. That's all you get. And now you want to optimize the policy to that. And we can just run all these surrogate objectives. The outcomes were actually quite interesting. So here's just sort of in the standard setup. There's too much going on here, but you'll notice these 3 clusters of things. I want to first just draw your attention to the top. The very first thing there at the top, so the orange bars are test error. Small is good. And the thing at the top, which does have the small, or the top 2 things, the thing at the very top is label smoothing. So this is the standard thing that's used now in supervised classification, maximum likelihood with label smoothing. Generalized as well gets like something like 1.3-ish% test error. I'm just using a fully connected, anyway. Okay, the reverse KL, actually after extensive hyperparameter tuning and whatnot, actually is very competitive. It's the second one. And then the 2 bars below that are, okay, the full expected reward, the thing I said that was a bad idea. Actually, it is a bad idea. This is not bad performance, but it's not state of the art, and that difference is usually enough for you to exclude something. But also that third bar from the top, which is not terrible, but still like 1.7% test error, was only achieved after extensive hyperparameter tuning. It turns out the expected reward objective is very touchy. There's all kinds of, so introduce offsets, fiddle with hyperparameters. If you really, really, really try, you can get it within sight of something reasonable. But it is actually very difficult to work with. The thing below that is squared error, which, is lame, and I guess that's good. We were hoping it was. Okay, now the group at the bottom are the first cluster where we just do self-imputation on those same objectives and just throw it at the problem. And of course, the generalization errors are much worse, as are the training errors, by the way. In fact, it almost looks like there's less overfitting going on. And they're kind of ordered the same way, is that, the state of sort of the predominant thinking right now is that second group from the bottom, the second bar from the bottom, is really, if you hyperparameter tune and you really try to drive down unbiased estimates of expected reward as the training objective and do your best to train those, you wind up at this mediocre end of things here. When you just do these simple, naive, like hopelessly, simple-minded self-imputation strategies, you get a little bit of an improvement. And then when I was about to walk away from all this, I tried all these hybrid things in the middle, which are almost always much, much better than any of these self-imputed objectives on their own. Most embarrassingly, there's sort of a tie in the middle between the first two there. Most embarrassingly, it's really, really hard to beat hyperparameter tune combination of expected reward and least squares. There's a really unpleasing outcome. Okay, so maybe it's anecdotal, maybe it's just MNIST. If you repeat the same experiment, same setup, but a much smaller training set size, so let's say 5,000 examples instead of 55,000, so really, really tiny training set, it doesn't really reorder things very much. Pretty much the same conclusions hold. Just one last thing I want to say about this is, okay, this is from a reward optimization perspective, maybe kind of a peculiar reward optimization problem because it's very sparse. There's just zeros and some sparse ones. What if you wanted to do something more interesting? So I just made up a fake task. Let's imagine we're doing MNIST again. There's a true target label. You guess a target label, and your loss is the absolute difference between those digits, right? So if the target's a 9, you guess a 0, that's 9. It's a dumb task, okay? But it's a dense reward function. There are big losses, small losses. It's got more structure, say. And we just mindlessly throw the same techniques at it. And this freaked me out. So we want small is good. That group, that hybrid group in the middle, in terms of generalization accuracy, is dramatically better. Like, this was not engineered. I mean, I'm just shocked by this. If we go to the small training set size, maybe things get somewhat compressed. But it's even bizarre to see that the supervised methods at the top are generally not competing against these partially supervised things in the middle, except for the label smoothing in the fully observed case is the only thing that seems robustly competitive. Wouldn't it be nice to have theory to explain all this? Well, I'll get back to that briefly at the end. Okay, so just anecdotal, but it's kind of weird that I'm discovering this now at this age. It seems like this should have been there back in the 90s. But let's take a lesson from this. What if it's the case that there really are surrogate objectives, that if you fit those objectives, that you really do get better generalization, that you can extrapolate your policy from a small set of observed data to a policy that is making good decisions well outside that data set. What can that do for us in the real problem we care about, which is sort of sequential decision making, full RL? Okay, so if we go up to the full problem, we just, same scenario, just log data. So somebody out there just logged a bunch of trajectories, right? You're X1, you took A1, you went to X2, you saw an immediate reward, R1. And yeah, somebody's going to want you to log proposal probabilities. I don't necessarily need to use them, but yeah, sure. So let's say we proposed, the behavior strategy and log those. Same problem. We just want to produce a myopic policy, a mapping from context to action. But no bootstrapping, which pretty much removes almost every technique you have been taught to think about first off. Okay, is this even possible? Well, yeah. So just conjecturing, what if we could use generalization to take the place of bootstrapping? If you think about bootstrapping, it is kind of like trying to take the place of generalization. It's trying to fill in some model of all the stuff you haven't observed yet, and then train to that. What about we flip it and say, you forget that, do sort of clean inference about things as best you can, and then try to exploit generalization instead of bootstrapping to kind of like go beyond the data. Okay, so we hit some challenges though. What are the major differences from the contextual bandit context to this context? Well, there's just two simple ones, and one of them is important as the first one, is that here the key thing in reinforcement learning is that the target values you'd like to regress toward are not given to you. They're actually subject to inference, right? The target value is not the immediate reward, of course, it's the expected future discounted return from taking this action in this state, okay? So you need some inference to even sort of set targets before you start minimizing loss functions. It's also the case that maybe losses should be sort of measured non-uniformly over the data. It's not clear that every state action tuple is equally important in a data set, for example. And so these are the two major differences in the sequential case from the one-shot case. But how about the following, just as a quick exploration? In terms of target inference, I want to avoid bootstrapping, so what I'm going to do actually is tabular. So I'm going to take the log data. I'm going to presume it's small enough that I can compute over it. That log data defines a partial MDP. I think it's often called a replay buffer, but I prefer to think of it as a partially specified MDP. It's an MDP where some of the rows in the transition matrix are empty. You haven't observed anything. But in most rows, there was a state action that you observed, and then you get a conditional empirical distribution over the next state. So you just build the empirical sparse partial MDP, and you can solve it. It fits in memory by fiat, and you can solve it in time and space that takes no more memory. You can just do some simple value iteration or something on that data, and solve for the max Q values. In large in large state spaces, probably that partial MDP just looks like a bunch of trajectories, and so max Q values are just Monte Carlo returns. Yep, so be it. Let's see what happens. And in fact, let's not even worry about weighting yet, because that seems to not help yet, but let's continue. So imagine the following procedure. We're just going to do this inference on the data to produce max Q values for all the tuples, the state action tuples. And then we're just going to optimize our policy using some surrogate objective on those tuples with target max Q values. And then we'll just evaluate that policy in the full domain. Okay, obligatory experiment one, just a simple 8x8 grid world. You start in the top left corner. We've got two distractor rewards and a nice reward in the bottom right. Some discount factor, expected horizon length 20. And look at different function approximation strategies using the strategy just as I showed you. I don't have time to explain too much here, but I want to draw your attention to the red and the pink curve at the bottom. That is just classical Q-learning with function approximation. The difference between these two plots is just one is using tile code features, and the one on the right is using literally the natural XY coordinates in the grid, copied for each action. So each action gets its own independent sort of XY coordinate system to learn some function. The red and the pink don't do well here. The thing you can't see in this plot is that Q-learning diverges every time in this scenario with just the coordinate features in a grid world with sparse rewards. Unbelievable. Anyway, and the difference between the red and the pink is the red is the typical textbook online Q-learning. The pink is do a rollout for a full episode and then do Q-learning reverse in time. You get slightly better inference. Doesn't solve the problem, still diverges. And then the other curves here are just the naive form of applying a contextual bandit objective minimized toward the inferred max Q labels. The gray, I haven't implemented everything here yet, but the gray is the expected reward. The blue is actually a policy gradient version. And then the yellow is least squares, and the green is the hybrid least squares expected. So the green is like the combination of yellow and gray. Okay, you don't see much here except that features can really help Q-learning, even if they don't help generalization that much, and I'll make that point more strongly in a moment. So just another quick demo, cart poll, which is a continuous state space. You'll never see the same space, state twice, etc. Imagine we're just doing rollouts with a random exploration policy. It will never get close to an optimal strategy, but we're just going to take that data and we're going to just optimize a policy based on that data and just see how well it generalizes and runs on the real domain. And it's interesting. First, I'll start with the good news picture on the right, which is literally just the coordinate features, the phase, so the x dot and the theta dot, the four-dimensional coordinate representation directly. What we start to see here is something that looks an awful lot like what we saw in the contextual bandit case, which is that gray line, that flat line there is the expected return of the exploration policy, the random walk. And what we're seeing here is the Q-learning variants actually are worse than random walk. Trust me, I've tried. It's not a bug, okay? You can get policy gradient to work well, but as you get more and more data, one of the things that happens with policy gradient is you get mode collapse, and it sort of fixates on a subset of the trajectories and forgets everything else. And actually, in the long run, it starts to overfit. And it's really hard to get this to repair. But what we start to see is the same kind of hierarchy of generalization effects where very naive algorithms that induce generalization in the policy are able to triple the expected walk time before failure and actually get most of the way, or a lot of the way toward an optimal policy without any exploration whatsoever, just random walk. So what we see on the right is how generalization has the potential perhaps to overcome the need for bootstrapping, to overcome the need for a lot of exploration, or at least to mitigate it. What we're seeing on the left, on the other hand, is very poor performance with tile coding, but tile coding does not generalize. The reason tile coding, one reason why tile coding might be very popular, at least in sort of early stage textbook stuff, is it doesn't generalize, but it stabilizes Q-learning. Do we really want to be learning features to stabilize an unstable core, or do we want to be learning features that generalize? And I would argue you'd rather do the latter. And I blew my time, but anyway, conclusions are, yeah, I don't know yet. It might work. It's speculative. Thanks.
Questions?
Hi, thanks for the wonderful talk. And I have two questions. So first, in the contextual bandit case, when you do self-imputation using doubly robust of the model output, wouldn't there be a risk of overfitting? Because in order for doubly robust to stay unbiased, the offset they use should be independent of data. And the second question, sorry, is the algorithm that you just described that use Qmax computed direct from data, it seems that you still need access to the online access to the environment for it to have any chance to converge to the optimal Q star. Because if you only use log data, it seems that you're only doing one step policy improvement over the data policy. Thank you.
Yeah, okay. Second one first. So yeah, if I give you log data and that's it, how are you going to guarantee you converge to Q star? Like, duh. Okay. So I guess that's not the point. But the fact is, in reality, we get finite data. And what we're really interested in is, would be more like finite convergence or finite error bars. Yeah, there's no analysis here yet, but I think you can. It's not clear it's hopeless. Just if you go back to the supervised learning case, right, that's exactly what you see, where you can get sort of uniform convergence guarantees that sort of give you, with high probability confidence, you're within some range of optimality. Of course, there are confounding effects here with the dynamics, but one could imagine, at least in benign scenarios, that you could push through some theory. The first point was interesting. Is self-imputation biased? It's subtle, right? So the fact is, for any fixed Q vector, it's unbiased. If you now have the Q vector itself dependent on the behavior strategy, then that would be broken. But if the Q vector is independent of the behavior strategy, the thing that we're taking the expectation with respect to, it should be still unbiased. I think there is no dependence there. Anyway, sounds like a subtlety. The other reaction I was going to say is, even if it is, say it's biased. Of course, I mean, I'm taking this unbiased estimate and plugging it into something that's biased, by its nature. So it's not as much about unbiasedness as it is about generalization, like transfer from the data to future state action pairs. Okay.
All right.
Ta-da.
The talk, yeah, it was after you set my expectations. It was awesome.
Oh, okay.
What can I say?
I'm being set up.
No, I do have a question about this idea of using different surrogate losses. I've also tried this a little bit and trying to do some theory about it. And my conclusion at the end was that, well, if you have a finite amount of data, it's going to be really difficult to know which of these is going to work better. So do you have some insight of like why we can get out? It seems to me that this is kind of a trap. So can we get out of this? So in the limit of infinite data, we have wonderful theories that allow us to choose between surrogate losses, but we always have finite amount of data. It seems like it's more like a model selection question than anything else. And then I don't know what you can do.
I have a couple reactions. One is you asked me to share insight, and I will just remind you that every prediction I've made about which surrogate will work well in whatever context was dead wrong. And so I'm a little bit nervous to say I actually understand what's going on. I have some speculations. But maybe I'll address the theory question a bit, which is some of these objectives you might hope would be consistent. That is, in the limit, right? That we would hope that if you could globally optimize some non-convex objective and in the limit get like true expected values, that you might be able to separate some of these as being consistent objectives that still sort of span the optimum, and others that are inherently biased or inconsistent that would like always have some irreparable bias. I haven't done that analysis, but that would be sort of one thing that would be worth doing. The thing I'll speculate about is they're all just surrogates. They're all trying to do the same thing, but they do seem to have implicit regularization effects, and they do seem important, and they seem quite different. So it's not regularization in the sort of the parameter space, but it's regularization in the response space. And it seems like appropriate regularization that still doesn't just needlessly diffuse, still keeps structure around optima, but otherwise, kind of it keeps you regular elsewhere. Seems helpful, but I only have vague intuitions about that at this point.
All right, let's thank Dale again. And